Housing is a very progressive.
All right. We'll welcome everybody as you come online. Give you a chance to get your Zoom tied in there. I think we're going to have quite a group this afternoon, Trevor.
Excellent.
Yeah. But, welcome to the Thursday afternoon Critical Canadian Home Building Science. Got a number of familiar folks coming on there. Mr. Bruce Kelly, some folks from DuPont Tyvek, Mr. Corey McBurney from Country Homes, head of sustainability. Very cool. I'm not going to be able to name all the other names because we're already up to 80. So anyways, we'll give them just a few more seconds here for folks to get on, and then we'll get started. You know, I think it helps when you put the word controversy into the headline, right? It's one way to get everybody to attend. All right. Well, you know what, Trevor, there's a lot of content that you've got for us today, and it is a robust conversation that I think we're going to have. I think we're just going to get started. So welcome everybody to the Thursday afternoon webinar. This is brought to you by Enbridge and Building Knowledge Canada. So this is part of our Critical Canadian Home Building Science series, part 7. So part 8 and 9 are coming up, and some of you will be getting notice too that we have a mini series, a 2-part series on carbon, what builders should be planning on to decarbonize beyond energy efficiency. So let's jump into the session this morning, the Great Canadian Vapour Barrier Controversy. And we have an expert with us this morning. But first, I do just want to recognize our sponsor, Enbridge, which has been so helpful in supporting these sessions, not just supporting, but encouraging good, robust, helpful conversations around oftentimes very complex, but very important topics like vapor control in buildings. Susan Cudahy, I don't know if Susan can be with us today, but Susan is the supervisor of strategic builder relations. Susan and team are working with builders across the province. And again, too, we've seen Enbridge start to engage on decarbonization efforts, even geothermal and solar, and lots of cool stuff that you'll learn about in future webinars. All right, folks, a couple rules of engagement this afternoon before we get Trevor started. Number 1, welcome. Please put your questions, topical questions today in the Q&A, in the chat. Please limit the chat functions for technical items related to, hey, my Zoom's not working. Stacy Cooper's in the background today at the Building Knowledge Canada webinar host. She'll help you with that if you have questions in the chat. There is going to be a Survey Monkey. It's going to come out afterwards, so please fill it out, get it back to us. That goes back to Enbridge, helps them and ourselves understand what's been helpful, what hasn't, what have we missed, what should we do next. And of course, Trevor has been very thoughtful and kind in that he is going to let us send out the copy of the presentation today, and recordings will be made available to everybody. So you will get this material afterwards. Stacy, do we have some polls for this one? I can't remember. Are we going to ask these folks where they're from today? There we go. So tell us, where are you calling in from? We'll see if you know how to use Zoom here. It's always like watching a horse race. It's like we got Ontario, but we've got some folks already from British Columbia and Alberta, Saskatchewan, Manitoba, Quebec, Atlantic provinces. Trevor, you're covering coast to coast today.
Cool.
Yeah.
Exciting.
Very nice. Nice to have some folks from those areas. Thank you. Let's the next thing we usually like to ask is so what's your role? So everybody give us a real give us a chance, give us an idea of what you do day to day. And if you're not listed on here, just put it in the chat. I see we have a number of building renovators, developers, excellent engineers, architects. We've got some site construction staff. You it's one thing, I guess, to talk as consultants, isn't it, and energy geeks. It's another thing to actually put your hands and build this. And Trevor, both you and I come from a background as builders, and it's probably some of the most practical we ever could have had, in the field.
Definitely.
So consultants, sales reps, mechanical contractors, building officials, and other. So we'll let the others tell us what that is over in the side. So it's good to have you folks all with us today. All right, I'm going to very quickly, many of you would know Trevor. Trevor's a good friend of our industry. Trevor's been working with a number of builders across Canada, president, building science specialist at Vapour Building Science. Trevor, do you want to introduce yourself real quickly, sir?
Sure. First of all, I do have more than one shirt, but not many more than one shirt. So I'm wearing the same one as in the photo today. I am the president and a building science specialist at Vapour Building Science. I've spent a lot of time working on the hygrothermal performance of wall and roof systems, especially in cold climates. So including air tightness, vapor flow, heat flow, all those things that are really important in the performance of a building. And when we get into the extreme cold climates, like some of my research has been in, all of these little decisions become, the consequences are even greater in those cold climates. So that's where I come from. And that's my background. The other thing I have done a lot of is forensic investigations. So when things go wrong, and so I always have that perspective too, as what could possibly go wrong here.
That's right. And you're going to share with us things that have gone wrong and how to think about maybe what might go wrong as you go into the future. So we real quick, we've got a real robust agenda, folks. We've got a lot of territory that Trevor's going to cover. I'm going to provide a little bit of color commentary, maybe pepper him with some questions. I'll be keeping an eye on your questions in the Q&A. Trevor and I are going to try to leave about 15 minutes or so at the end of the day for QA. But even if we don't get your questions, we're going to try our best to provide some answers even after that. So I'm going to do a little context setting. One of the things I've always, struggled with as a builder too is where did vapor barriers come from and air barriers, and why can't we get our language right? Like, is it one or is it the other? And oftentimes today we're talking about poly and we call it a vapor barrier, which it is, but really what we're most concerned with is its air barrier properties and what came first, air barriers or vapor barriers. So a little quote, number one, when we forget the knowledge of our history, even here in Canada, the things that those that went before us around the building science and the National Research Council, we will become like a tree without roots. We forget why we even have references to air barriers and vapor barriers and what actually is most important. So I thought I'd do a little bit of context setting. So why do we see vapor barriers or concepts of vapor control earlier than air barriers? So diving into a little bit of the work that work that was done at the National Research Council, the development of the Building Science Digest, one of the things we do know is back in the early 1900s, we started to stick stuff in houses like, rock wool insulation. And actually that insulation you're seeing there is horsehair. And we wanted homes to be warmer. I mean, it wasn't to save energy. There weren't greener homes program. We stuck in walls because it made us more comfortable. And when we did that, stuff started to happen. We started to have spalling of brick and stone. We had paint started to peel. And based on some of the history, the scientific accounts of the day was the science people were able to identify was that we had freezing water vapor now happening. We had made the walls cold. We had somehow changed this, and that there was this excess wetting now that was taking place, and it was causing this spalling and the damage to the structure and to the cladding. But the big thing was we didn't know, we knew it was water vapor, but we didn't know how it moved or how it was transported. So we sort of thought, well, it's vapor diffusion, but we also sort of lumped in air transport with it as well, but we continued to call it vapor barriers. So really it was the airborne water vapor wasn't understood until the 1960s. And really we start to see that in the history of the Canadian Building Digest. And if any of you don't know what the Canadian Building Digests were, and you consider yourself building science geeks, you need to spend a weekend with these digests. They are the sort of the preeminent articles that were written back in the day by some of the godfathers of cold climates building science. You had, Handegord, Hutchin, Grant Wilson. You had all these names, of course, that, we've heard about for years. That great book, Trevor, the NRC Building Science for Cold Climates, this sort of groundbreaking and still used today manual. A lot of, you'll see in the back of this book actually are some of these articles. The interesting thing about these articles was, I believe the challenge was the authors could not use more than 2,700 words to write these articles. So they're no longer than 4 to 5 pages, and yet you find in it the history of a lot of this. And anyways, one of the things that was identified in there was that, and this was Gus Handegord wrote this about the history of this, was that they looked at vapor diffusion first, but they also had some cautionary notes about this condensation that was occurring, that maybe it had more to do with air leakage. And they actually started to see this with some of the studies around windows first. And one of the things he noted here in this writing was it was the role of air exfiltration in causing condensation. It was first reported by Canadians in the 1950s and sort of the 1960s. So air barriers, or airborne transport of water vapor, actually came after this concept of just vapor barriers, and took us a little while to get it straightened out. This is from the first building science, CBD number 23, that Grant Wilson wrote. And this was about air leakage in buildings. And he makes a reference in here I thought was sort of interesting. He says, the extent to which it is responsible for serious condensation. And this is about air leakage. Unfortunately, this is largely unrecognized, and this again, 1960, in the design and construction of many buildings. Even when the failures develop, the source of moisture is often incorrectly identified. Again, was it diffusion or was it air leakage? So
somebody asked for the title of the book, so I'll just hold up my copy for a bit.
There you go. Yeah, actually, we'll NRC, and again, we can send this out, Building Science for a Cold Climate. And again, it was from some of this work. Many of you would recognize this slide, right? We learned about vapor diffusion, but it wasn't until the 50s and 60s that we started to understand that, yes, it's important. But how important is it? And, here it shows that there is diffusion through a wall over the course of a heating season, a liter of water that can go through a 4x8 sheet of typical gypsum. And again, a liter of water is still a liter of water. But again, we then moved on to learn that actually it was air leakage then that really carried the bulk of the water vapor into the wall. So it took about, what are you going to say? Probably about 50 to 60 years to get from vapor to air leakage and to air barriers. And then it took us another 15 to 20 years, I guess we're sort of slow, to actually get air barriers into the building codes. And the amazing thing to me is that was only circa 1990. When we started to have air barriers in the code. And it wasn't until 2012, which is interesting, in Ontario, that air barriers was actually a required inspection. And yet, here's the thing, the point we want to make is that air is the cause for a lot of condensation issues and durability issues. And again, we always like to remind folks that, air barriers, a lot of these seminars we've been on, we often talk about air tightness and air barriers as a energy thing, but really when we look at the National Building Code, the item that is at the top of the list it's to limit condensation, interstitial condensation. So I'm going to wrap this up and I'm going to move it over to Trevor, but I just wanted to sort of set that a little bit of context, because in my mind, it's always been a struggle because we mix the words up. Vapor barriers, air barriers, we get their context mixed up. We forget which one's most important. And so what we're going to try to do today, Trevor, is I want to have you talk to us specifically about vapor control. And I think one of the things maybe we want to come out of here today is there some better ways that our codes can deal with vapor control terminology? Are there some better ways that we can look at vapor control strategies as opposed to thinking about it as poly. I'm so sick and tired of going to the job site, seeing issues like you've brought up where we've got condensation behind the poly, and it seems like that's all we can think of. So Trevor, I'm going to leave it with you, and here's some of the topics you're going to hit on, so take it away.
Great. I will share my screen.
All right.
Not yet. 1 second. Yeah, it's funny because I don't spend a lot of time in my consulting practice talking about vapor flow, really, especially on the the side of when we see damage, it's almost always related to air leakage or water leakage from the exterior. And so don't spend a lot of time talking about it, but it is an important issue and something that was worthwhile for me to do sort of a deep dive on to help put this presentation together. Can you see my first slide there, Andy?
We can, yeah.
Excellent. So this is the grade 9 science portion of the presentation, in which we kind of talk about, well, we're talking about vapor. We're talking about vapor movement. What is vapor? Vapor is water molecules that are suspended in our air as a part of our atmosphere. So if we look at what the atmosphere is made out of, it's mostly nitrogen, a bunch of oxygen, some other inert gases, and then there's all others, which is a very small sliver, and within that is another small sliver, which is water molecules. And the important thing to remember is that when we talk about vapor flow, we're talking about the movement of water molecules. We're not talking about anything you can see. We're not talking about a water droplet, okay? It actually takes, this blew my mind. I still can't quite wrap my head around it, but it takes 1.67 times 10 to the 21 water molecules to make one water droplet.
Wow.
So I couldn't possibly draw that to scale on my slide, but you get the picture. Even when you see steam in the air or fog, those are water droplets in the air. Those aren't water molecules, okay? You'll never be able to see a water molecule in the air, and we're going to try and understand how they move and how it's different than water droplets and liquid water, which we mostly deal with in building science.
Yes.
So what is vapor diffusion? Vapor diffusion is the net movement of water vapor from an area of high concentration to an area of low concentration. In this little simple model, okay, we've got an area of high concentration on this side of our box, a material separating it, and an area of low concentration. The reason I say it's the net movement of water vapor is because each of these water molecules is just randomly bouncing around. These ones are, and these ones are, and eventually one will find a way through our material that's separating, right? So there'll be some movement of these through to this side and some through to the other side. But because we have a higher concentration on this side, the net movement over time will be in this direction, okay? Until eventually this hits an equilibrium where there's equal water molecules on each side. So remember, it's random movement, but it can be directional if there's a vapor pressure difference. So how can we, what are the things that affect the rate of movement? The first one we'll talk about is vapor pressure. So if there's a greater concentration on one side than the other, there's going to be a greater rate of movement, net movement from one side to the other. So you can see in the other case, now we have a lot more water molecules on this side, and they're going to move more quickly to this side until we reach equilibrium. So when we talk about vapor pressure, it's literally the number of water molecules in an area, and movement will always occur from high pressure to low pressure. What else can affect the rate of movement through a material? Basically the vapor flow resistance of that material. So if we double the number of holes, so on quote unquote holes in this material, holes that are big enough for a water molecule to go through, we'll have a greater rate of movement from our area of high concentration to our area of low concentration. And those are really the two big things that affect the rate of movement across a material. Obviously, when we look at this, remember these holes aren't big enough for a water droplet for sure. They're not even big enough for air to flow through under pressures that we would see in a building. These are only big enough for a water molecule to go through. But in reality, when we're talking about buildings, we don't just have one material separating inside from outside. Sometimes we do, but usually we don't. What we usually have are several materials separating inside from outside. In this case, we have a wall cavity. Okay, so let's say we have a high concentration of water inside our building. We have a low concentration outside, and we'll talk about, why that is and what kind of magnitudes we'll get.
Hey, Trevor, we can actually see your notes. I mean, I think we're okay with
Okay.
that, your speaking notes,
The
but
next slide thing, yeah.
it sounds
I'll
good.
make them smaller.
Beauty.
I'll know what's coming, but too much away.
Awesome.
So what we have in buildings typically is a wall cavity or a ceiling or roof cavity. And then what really matters is how quickly are these water molecules moving into the wall cavity and how quickly are they moving out. If they can move more quickly in than out, we're going to get an accumulation of moisture, of water molecules inside the wall cavity. And so what does that look like? So now we have equilibrium. We're going to reach equilibrium much more quickly from inside to the wall cavity than we are to the outside. And so we end up with high levels of moisture inside the wall cavity if we don't stop it here on the warm side. Why is that a problem? Because in reality, again, the wall cavity is not only is there a different number of water molecules across this, there's also different temperature gradients going on. So in reality, we have a warm surface here and a cold surface here, if we're talking about a winter condition. And if we allow too much moisture to accumulate inside this wall cavity, we'll get condensation. And we'll go through a bunch more examples to make a bit more sense of that over the course of the presentation. So right now we're talking about vapor pressure, right? What's the difference between vapor pressure and relative humidity? Well, relative humidity we're a bit more familiar with. It's a measurement of the amount of moisture contained within air, but it's relative to the maximum amount of moisture that the air can hold. So that's important because the maximum amount of moisture that air can hold is a function of air temperature. At cold temperatures, air can only hold a small amount of moisture, whereas at warm temperatures, it can hold much more moisture. And so relative humidity tells us how close we are to saturating the air, but it doesn't tell us the absolute number of water molecules in the air. To do that, we need to talk about vapor pressure. So vapor pressure is the measurement of moisture contained within the air in an absolute sense, regardless of air temperature. And that's really important when we talk about vapor flow, because vapor doesn't flow due to RH or relative humidity differences. It flows due to vapor pressure.
Vapor pressure, right, yeah.
So you can have cold air with a very high relative humidity, but it can still have a very low vapor pressure. Whereas if you have warm air, even with a lower RH, it can have quite a high vapor pressure. That's because the relative nature of it. And we'll talk a bit more about that next, as I can see in my slide coming up. When we talk about the relationship between temperature and moisture, we have to talk about the psychrometric chart. This isn't something that we're going to get into in detail here because it's really complicated, and this chart can be used in many different ways, but I'll talk about the way we use it in one way. What you really need to know here is that temperature is across the bottom here. So from -25 to 55, and then vapor pressure runs up here. And this particular one is in millimeters of mercury, which is a whole other thing when we talk about the confusion around these topics can often occur because we use different scales and different things. But in this case, we're just looking at relative things. So each of these red lines represents a different percentage of relative humidity. So there's the 10% relative humidity line as it goes across different temperatures. There's the 70, etc. So why is that important? Well, let's look at one condition. This is the condition of Toronto in the winter. So if we look at our outdoor air, let's say it's at -5, and it's at, let's say, 90% relative humidity, right? So that's really high, really cold air. But the vapor pressure that creates is actually quite low. It's only, in this scale, 3 millimeters of mercury. When we look at the normal conditions of indoor air, we're talking about 20 degrees Celsius and let's say 40% relative humidity. And we have a much higher vapor pressure. Right. So in this case, we have a vapor pressure difference of over 500 pascals outward. So the drive is from inside to outside in the winter.
And is it the same, Trevor, if you were going to calculate how much water vapor would move through would be the delta between the two.
Yeah,
That would be
exactly.
part of that calculation, correct?
Right, exactly. So your pressure difference is a big part of the calculation as to how fast vapor moves.
Okay.
Exactly. So this is Toronto in the winter. Well, let's look at somewhere colder. I just picked Winnipeg as an example. In Winnipeg, let's say we got a -20 day and it's 95 or 100% humidity even. But because of the way these curves work, we end up with actually a very low vapor pressure, less than 1 millimeter of mercury pressure. And we have the same interior conditions, 20 degrees Celsius, 40% RH, and it creates the same vapor pressure inside. But now this difference is a lot greater. It's over 860 pascals. And again, that's outward. So higher pressure in the building, lower pressure out. The vapor is trying to move through the walls, through the roof in every way it can to create an equilibrium from inside to outside. Okay, so that's why climate matters. Colder places like Winnipeg will have higher vapor pressures and will have different requirements for vapor barriers than Toronto will. That warm, southern climates will for sure. Yeah. The other thing that we have to think of, those are just the winter conditions. That's just one point in time in the winter. Let's real quickly look at Toronto in the summer, just as an example. So interior conditions, let's say now we're like, we let it get to 21, 22 inside, it's air conditioning time. And let's say we can keep it to about 60% relative humidity with our air conditioning system. So now we have something close to 13 millimeters of mercury vapor pressure, which is higher than anything we saw before. But what about our, what about our outdoor conditions? Our outdoor conditions might be 25 degrees Celsius and upwards of like 70% of humidity in the summer. And that's creating 18 millimeters of mercury, which in, the pressure difference is actually quite great. It's 730 pascals, but it's in the opposite direction than it was before.
But we just put the poly on the inside though, Trevor. So
always put the poly on the warm side of your house.
Oh, yeah, that's right. It just goes back and forth.
As long as you move it between seasons, you'll be fine.
Yeah, that's right. That's interesting. We've been made aware of some studies in similar climate zones, I think in Chicago, where they, areas of the Great Lakes, higher humidity levels, where they are seeing issues with air conditioned residences, that with these warm, humid environments in the summer, they're seeing condensation on the backside of vapor barriers in the home. That's something we have to be very aware of as we go forward.
Yeah, and with climate change, one of the biggest changes we're seeing are more air conditioning days and places that now need air conditioning that never had them before. So we're really going to be changing the dynamics across the walls of in different places in Canada as we run air conditioning more and in places we never did before.
Right. Yeah.
Yeah. Good. And so that's a reversal of vapor flow from winter to summer. And so that makes things difficult, right? What does that look like? So those are just moments in time, but what does that look like across the course of a year? And I seem to be stuck. Oh, there we go. They're going to all go at once.
That's all right.
Yep. Let's go back. Okay, one more. And one more. Okay. I can't tell what's mine. There we go.
There you go.
So if we look at hourly data across the course of a year in Toronto, the blue line is the exterior vapor pressure of a typical cold year in Toronto. The orange line is the interior vapor pressure in Toronto. And again, this has a lot of assumptions in it, but this is pretty normal, 40% relative humidity in the winter, 60 in the summer, et cetera, et cetera. What we see is that most of the year, 86% of the time, we have vapor pressure trying to get from inside the building to outside. But we have a considerable amount of time, 14% in this case, where the vapor is trying to drive from outside to in. And so that can change over time as climate changes too. And those are the kind of things we start to worry about when we put this poly sheet on the inside of our building is, what are these what do these differences look like at different times of year? How does it add up across the year?
You know, one other thing, Trevor, we were noticing some things south of the border in their new IECC 2021. There's been a sort of a rejigging of some of the climate zones, the ASHRAE climate zones. And we've noticed that there's actually some large demographic areas that have actually slid a climate zone to the south. Now that's very complex, right? Now these things are playing a huge impact on the wall. Where do these things belong inside of the assembly? Anyways, keep going.
Yeah, and even how you define climate zone matters, right? We typically used heating degree days.
Right.
But what we're seeing with climate change is we're still seeing almost as many heating degree days, but now we're seeing more cooling degree days.
Right. Yeah.
And so maybe just using heating degree days isn't the best way to figure out climate zone going forward. I don't know. So back in the day, we had these monolithic walls, right? We had these 3 wide brick, stone, solid wood walls, and we never had any vapor barriers on them, and we never had any problems with them. And there's a pretty good reason for that. So if we look at the conditions inside, right, and the conditions outside, at some point we have to get through this wall from 20 degrees Celsius to -5, from 40% relative humidity to 90, and from 850 pascals of vapor pressure to 370. And so the pathway that we get from A to B really matters. And when it comes to a monolithic wall, it's super simple. There's just a linear change as it goes through the wall. So as temperature drops, so does vapor pressure as we move across this wall. There's no reason for anything to jump up or slow down or go faster, because it's one material essentially, right? They all acts that way. And we look at our relative humidity. There's no reason for this relative humidity to ever jump up over whatever it is outside. And 90% relative humidity is a really cold, dry day. And there's no real reason for it to find anywhere greater than or reach anywhere greater than 100% relative humidity in these monolithic walls. And that's why we never had problems. The other thing we don't see is these walls probably had like oil-based paints on the inside too, which acts as a bit of a vapor barrier. But even if it didn't, we still wouldn't really see problems.
Yeah. And materials that were good at storing, they had a higher water storage capacity than, let's say, wood or paper-based products, which we build with today.
Yes, yeah. The other thing, Andy, there was a picture you had of some brick, painted brick, and all the paint was falling off.
Yeah.
So imagine we put a coat of paint on the outside of here that had a greater vapor resistance than the brick itself did.
Yeah.
Now there's a reason for this to get up above. We're going to see a large drop in our vapor pressure across that paint layer, and we can get greater than 100% relative humidity on the backside of that paint.
Of the paint, interesting. Yeah.
Drive it away. It's going to remove it from the building with moisture. Right. And so as we change these things, even in small ways, we have to really think about the consequences. Then as we started to build stick-framed buildings, my house is from, I think, 1915, balloon-framed, dimensional, probably true 2x4 lumber, and board sheathing. My house has board sheathing with gaps in between the boards. It originally had no insulation, so let's look at that case. And we still have the same conditions inside and outside. And how do we get from A to B? Well, temperature, because we have no insulation here, air is about as good an insulator as wood, and we still get a pretty steady drop across in temperature. But when it comes to vapor pressure, now we've got this plaster on the inside, okay, which at least has some vapor resistance compared to air. So you're going to get a big drop in vapor pressure, and it probably also had oil-based paint on it. So we're going to get this big drop in vapor pressure across that paint and plaster layer, and maybe a little bit of a drop across my sheathing, because it is wood, which has some vapor resistance, but it's wood with a bunch of gaps in it. But most of my drop is going to happen right here through this layer, which is, where you want it to happen, on the warm side. So really the RH is going to drop actually as it goes across this layer. It's going to come up as it goes across this cavity, because it's getting colder and colder and colder as I go. So my relative humidity is going to go up. But the chances are that that's not really going to get above 100% before it drops back down to the outdoor conditions. It may once in a while at the coldest days, but this is, in this case, like rough cut, solid wood. It can handle some moisture, store it, dry it later, no problem. So we didn't tend to have these problems in these uninsulated wood walls. And that's why.
Uninsulated.
Uninsulated. That's why it's white versus pink.
There you are.
So here's the same wall, except I've decided, oh, I got to get rid of this old sheathing. It's really old. I want to get rid of it. So I'm going to put OSB on here. And, oh, I'm going to get rid of this plaster. I'm going to put drywall on, let's say. And I'm going to, oh, while I do it, I might as well put some insulation in there. So how does that change the wall? Well, the temperature profile actually looks about the same. We still have that steady drop across the insulation layer. The biggest difference now is that my vapor pressure, I'll get some drop across here. Painted drywall has a little bit of vapor resistance, but this OSB layer has way more. And most of my vapor pressure drop is going to be across the OSB, which means that even though my RH is going to drop a bit as I go through here, it's really going to get up really high as it moves across this wall. And it's very likely a lot of the year, I'm going to have 100% relative humidity right here on the back side of the sheathing, because I basically have a cold side vapor barrier now.
Right. And that's where those spoons are, right? The famous spoon curves that show the condensation risk on the backside of the OSB, during parts of the year. And those are typically given at assumed rates. So the code would assume 35% is the average relative humidity, 20% set point. And it's not saying that it's always going to have condensation, but there's that risk of having it. And it's, we often see it in the field as frost on the backside. But again, if it's wet enough for long enough, then yeah.
Right. And then what happens when that frost melts? Does that water have a way out? Can it redistribute? Can it dry out? And we'll talk a bit more about that with regards to poly. But again, all of these diagrams, that's just one moment in time, right? It's just like, here's the cold day. Really, when we start to look at more complicated issues related to actual weather on the outside and changing conditions on the inside, we have to start looking into hygrothermal modeling, which I'll talk a bit more about.
So using something like WUFI, looking at the storage characteristics of the entire assembly, how long it's there, indoor, outdoor conditions, sort of that total climate regime from the inside to the outside, the conditions.
Yeah, and what happens to, how fast does this material absorb the water and store it, or does it stay on the surface and run down and collect down here? All these things are very complicated, and we can capture a lot more of them with modeling than we can with these sort of static drawings, but I think they're really useful teaching tools. So how do I fix my house here? Let's say I did this. I didn't, but if I did this, I'm going to have all kinds of water running down here. Well, what we've done as a society is said, well, we need a vapor barrier. So if I put a vapor barrier in this wall behind my sheathing, that changes everything again. All of my vapor pressure drop almost is going to happen across that layer. So now my relative humidity, as it starts off much lower and ends up lower, and I'm now in a safe zone because of this vapor barrier and the fact that I've slowed my vapor transmission so much at the warm side of my wall.
Okay. But again, this is not looking at airborne transport, right?
Exactly.
This is just simply vapor diffusion based on vapor pressure differentials.
Exactly.
Okay.
As soon as I poke a hole in this, if I poke a nice hole in this, it's not going to change this analysis much at all. But what it is going to do is promote air leakage, which can put a lot more moisture into this wall than vapor flow can. So yeah, it is weird for me to only talk about vapor flow.
That's right.
Because it's rarely the problem, but it can be. So when we're talking about different materials and their resistance to vapor flow, there's some terminology we need to understand because it gets really confusing, to be honest. And I still have to look things up at times and remind myself what's going on. So there's two different terms we need to understand: vapor permeance and vapor permeability. They sound the same, but they're actually slightly different. Vapor permeance is a layer property. So it's a property of a given layer. And it's really good for describing the vapor flow resistance of membranes, something that's thin, or something that's maybe a composite material. Maybe there's two materials here that the thickness isn't really as relevant as what the total vapor flow through that material is. It's also good for homogeneous materials. I use spray foam as an example. And we always have to make sure that, did I say that wrong? I did, I'm sorry. So the fact that it's a layer means that no, see, I've already confused myself.
That's right.
My slide. So because it's a layer property, we don't care about the thickness. We're talking about the material, no matter how thick it is. It can't be used to calculate or predict the performance of that material at different thicknesses, right? So for example, this is zip R, right? I can't just double, if I add more EPS to the back of this, I can't just, cut the vapor permeance in half, because there's different materials in the material that have different vapor permeances.
Right.
So I'm really describing this whole thing. Same with Tyvek. It's so thin, I'm not going to have thicker Tyvek or thinner Tyvek probably. It's a good way to describe it in vapor permeance. When it comes to vapor permeability, we're talking about the property of a material. And the difference being is that when we use vapor permeability, we're assuming a thickness of 1 meter of that material. And so it can be used to predict the performance of that material at different thicknesses. So if I know what the permeability of concrete is, I know what it is at 1 meter, then I can calculate what it would be at a 0.5 meter or at 10 centimeters.
Right.
So I need to know the permeability of a material like that so that I can turn it into a permeance with its known thickness. And it could be the same with a brick. EPS is another good example because it's so, as long as it doesn't have a facer on it, it's so homogeneous that if I double the thickness of it, I've cut the vapor permeance in half. And those are things we can calculate. These are either too thin, or because they're made up of different materials, I have to describe them as a material, not as
almost as a system. Yeah.
As a system versus a material that I can just play around with the thickness. I thought I had that really well laid out to explain to you, and I've kind of confused myself as we go. So it does get confusing.
That's all right. It's like that difference between the U values. What is an actual U value? Conductance of the assembly or just something?
Exactly. Conductance, exactly. And now, just to make things even more confusing, there's a bunch of different units that are used to describe the vapor flow characteristics of materials. In Canada, we use SI units. And the SI units for permeance are always in nanograms per Pascal second meter squared. Seems complicated, but actually makes sense. That's why I like this, because nanograms, a small measurement of weight. So that much water, how many nanograms of water go through a material at a given pressure in pascals, given vapor pressure, over a given time, a second, over a given area, meters squared.
Right.
So it does make sense, but it looks complicated at first. And these are the units that are used in OBC, NBC. So these are, we always have to, if we see some other units, we can't directly compare it to what's in the
And
OBC.
we have seen that mixed up in some engineering reports.
Yes.
Yeah.
Exactly. And so permeance, on the other hand, that should be nanograms too. The difference between, again, permeance and permeability is now we're talking about for a meter. So really it's in nanograms. So I'll have to change that. It's supposed to be NG, nanograms of water per Pascal of pressure per second per meter of thickness.
Right.
So it's not M squared anymore. It's meter of thickness, which can be also very confusing and easily you can make a mistake.
Yeah.
The way I like to think about this though is nanograms per Pascal second meter squared, just like permeance per meter. But it's always expressed this way because it's a simplify. That's how you simplify out the mathematically, how you simplify out the units.
Right.
Because meters squared over meters brings you back to meters. So this is the way I like to think about it though. It's the same as permeance, but it's for a meter of thickness of a material. And if you want to try and compare a material that's where they give you the permeability to the NBC or OBC, first you need to multiply that material by its thickness in meters.
Right. Okay.
And then, okay, that seems to me like I can wrap my head around that, but here's where I start to kind of lose it. There's something called a metric perm. I thought SI units and metric were the same, but apparently they're not exactly the same. So this is the SI permeance. This is metric perm. Metric perm is in grams per day, per meter squared, per millimeter of mercury.
Ah, oh boy.
Just,
okay.
I think it's just done to confuse people, to be honest.
Yeah. Yeah.
So if you see anything that's listed as something metric perms, you need to first convert it to SI units before you can compare it to the OBC.
Right. Okay.
Okay, so that's all in under metric. Well, what happens when we get to imperial units? I think the most common term used in the US for this is perms, which actually should be called and is sometimes called US perms, but is often short form to just perms. And that's in grains of water per hour, per square foot, per inch of mercury. Not that that really matters, but just to know that this is permeance, just like this, but in imperial units.
And I think this is important because we often we'll get an architect or a client that'll say, the manufacturer told me this has so many perms. Yeah. And I'm going to say 75% of the time here in Canada, the reference is the US based perm. So we then have to step back, go back into the literature, go look for and do the calculation. Because again, you can really send yourself down a rabbit hole if you don't. So
yes. And these are the units, US perm, but they just call them perms, that are used in the IRC, the International Residential Code, that we'll talk a bit more about later. Yeah. And then perm inches is just the permeability version in imperial, grains per hour, per square foot, per inch of mercury, per inch of thickness.
Okay, good.
So anyways,
so we got about 30 minutes, just to give you a time table.
Yeah, I don't want to get too hung up on that. How do we come up with these values? People in labs come up with this based on two different tests. They're both different versions of ASTM E96. One is called a wet cup test, where we have a container filled with water that has a test sample on top and is kept in a chamber at a very specific vapor pressure. And we weigh this sample at regular intervals and see how quickly the water that's in here is leaving the container. So that's a wet cup test. There's also a dry cup test, which is the same thing, except instead of water, we put desiccant in here to try and create a zero RH, zero vapor pressure condition. And we see how much water comes from the air in the chamber into the material and into this container. So we weigh the container at intervals, and that's how we come up with these numbers that we see going forward. Okay. It's really important to note too that in the OBC, they specifically say use the number from the wet cup test.
That's and in right.
The IRC code, they specifically say use the number in the dry cup test.
Yes, that's right. That's right.
So the subtleties of this start to get really complicated, unfortunately. So what are some common materials? This is probably more practical stuff. If we look at the red line here is our OBC NBC requirement, which is 60 nanograms per burr. Let's look at some common materials. 6 mil poly, which is what we commonly use as vapor barrier, is like 1,000 times less basically than that.
Poly is 1,000 times more impermeable than it needs to be qualified as a vapor control layer vapor barrier.
Exactly.
And the only reason we're using it was because it was strong enough to act as an air barrier. Right. But it's 1,000 times. Right. Yep. Okay. Yeah.
And it's strong enough, it works that way. Right. Now we'll start to eventually talk about some alternatives like vapor barrier primer, which should probably be called vapor retarder primer, but that's fine. Yes. You know, and it's sitting more at the 30 nanogram area. Even something like 1/2-inch plywood or OSB are at about 20 nanograms. So again, a half to a third of the NBC requirement, or OBC NBC requirement. One specific example of a smart vapor membrane is certainteed membrane. it sits just below the requirement. I think it was designed just for that purpose. 2 inches of closed cell 2-pound spray foam, probably around 30, 35. So that meets our requirements. Things that don't meet our requirements, 1/2 pound spray foam, 2 inches of unfaced EPS would meet. 2 inches of XPS would. So like, you know, polyiso, again, if it's unfaced, doesn't meet our requirements, but foil faced obviously would, because it has foil face.
And again, Trevor, just to clarify, this is for the dry cup.
These are all rough dry cup.
Yeah, rough dry cup. So
yeah.
So if you look at this, you go, oh man, OSB it's a vapor barrier, but we put it on the outside. Well, hold on a minute. If you actually do this under wet cup, the permeability increases because the cell structure starts to open up. And that's really what you're seeing there with that, certainty membrane, which is, I think, now called in the National Building Code a variable perm vapor barrier. Anyways, and it under those wet cup conditions, 50% on one side, 100% on the other, it starts to open up and allow the transmission of water vapor through it.
Exactly. So, and plywood and OSB operate very much in the same manner, which is interesting.
Right.
Although we almost never use those on the interior. So
okay.
So we need vapor control, but we don't need a vapor barrier. We don't need poly.
Thank you.
This is where we're going. This is where it's all coming down. And what I've done here is I've run a series of hygrothermal models just for demonstration purposes. And what I'm showing here is the moisture content of the sheathing at different times of the year. And anything above 20% moisture content means we have a risk of mold growth and rot. And so what I'm showing here first is Toronto weather and a 2x6 wall with bad insulation and drywall, but no vapor barrier whatsoever. And what can happen if we have no vapor barrier whatsoever is we're going to collect a whole lot of moisture in this wall over the course of one winter. And that's not good. We can't have that. If we were to throw our poly layer in, obviously, it just flattens that line right out. We get no moisture in the wall. Okay, that's good. But what about some of our other options? If we look at vapor barrier paint in Toronto, you can see that it does rise up a little higher than poly, but still stays below our 20% threshold, the one we're worried about. And the other one I threw in is, what if we had no vapor barrier, but we added R10 XPS on the outside of the wall? It has a very similar effect. It does reach 20%, but just barely.
Just barely. So again, that's where you get into those inboard outboard ratios. And we'll talk about that in a minute. Is okay. So say it is low perm, but what if you control the first condensing dew point? So now you're into that. Okay.
When we add insulation to the exterior, where now the wall thinks it's in a warmer climate, and we can get away with things that we couldn't get away with before, right?
Right. Yeah, I like that. The wall, you make the wall warm. Warmer climate.
We just move the whole house to Tennessee or something. So that's the effect. The other thing I wanted to point out, though, is that while in Toronto, with vapor barrier paint, we're able to stay below 20%. If we were to do that same approach in Ottawa, we actually spend quite a bit of our winter, almost the entire winter, over 20% moisture content.
Okay.
So climate matters there too. So we have to be careful and realize that what works in Toronto might not work in Ottawa or Winnipeg, and definitely not in Iqaluit or Yellowknife.
Right. And I'm guessing that is because you go from Toronto, which is basically a zone 5 ash rate zone, climate zone 5, heating degree days. You move to Ottawa, which would be more zone 6. You have the temperature change increases the vapor pressure.
Yes.
Right. Okay. Yes. Okay. Interesting.
So you have higher vapor pressure difference, but you also have more of the year where the backside of the sheathing is cold enough for condensation.
Cold. That's right. So if we should be putting exterior insulation anywhere, it should be Ottawa.
Exactly, which I think is what I did next. That's my example. Oh, in this case, I put R5 exterior insulation with vapor barrier paint.
Nice.
And that's the dark blue line.
Nice.
Yeah, and just to note, I tried one with only adding R5 and it was still bad. So you
Okay.
can't just add R5 like you did in Toronto. It worked. It doesn't
That's
work.
right. That's
But
right.
if you do
Yeah.
both, you can do both here. Oh, I've got one more example. I'm not even sure what it is. Oh, I'm going to talk about interior conditions. Okay. So the other thing that matters, other than climate, is what's going on the inside of our buildings. We usually make assumptions about residential buildings, but we have to be careful of when those assumptions go wrong.
Yeah.
So in this case, what we're looking at is a Toronto wall with vapor barrier paint, just like we talked about before. That's the gray line, stays below 20. If we have low interior RH, let's say we keep it below 30, everything even gets even drier. But if we allow it to go up into, I think, up to 50 in the winter, let's say this building has a grand piano and it has to stay at 50% RH all winter. All of a sudden, our vapor barrier paint's not good enough to keep us below 20%.
So this is where that complicated discussion during COVID came in, right?
Yeah.
You had everything to do with, washing your hands, distancing, ventilation rates, but then we also had this new concept reintroduced to us about maintaining relative humidity. And that concept that we've known for years, that when you let the relative humidity get down to 20%, that you become clinically dehydrated in most cases. So what is the good? And so again, there's a lot of champions out there saying we should be keeping it at about 35 to 40%. And I think it's something, not that we want to go out and change the codes and bump it from 35 to 40, but I do think it's incumbent on us in the building industry to think ahead on those things. We can't expect people to maintain their homes at 15 to 20% because it's not healthy. No. But is there a way that we could build walls, make windows, hint, hint, better windows, that don't get condensation on them when we have healthier ranges of relative humidity, ergo 35 to 40 in the winter?
Yep. More exterior insulation and better windows and better air tightness. That's how you do it. Right. Yep. Had to throw that in too. So poly works and stops, our outward vapor drive. So why don't we just use it all the time? Well, there's a few problems that can happen. As we mentioned, the vapor flow resistance of a poly sheet is about 1,000 times higher than even the OBC NBC requirement. It can result in condensation due to inward vapor drive in some cases. Below grade walls, so basement walls is a big one. And even in walls that have moisture storage cladding, like direct applied stone veneer, depending on how wet that gets when the sun hits it, we can have condensation problems due to inward vapor drive sometimes in those conditions.
So
yeah.
Well, I'm gonna swap the screen for him because I want people to see this. Because I don't think that there's actually, I think there's some people in our climate that don't believe this happens. So I want to share something with you folks.
Sure.
I'm going to show you a picture. We see this a lot. I see it in buildings all the time. What you're seeing on this slide is condensation occurring behind the poly. The basement, it is not because of excessive air leakage. This happens, and it typically happens in the spring, is you are now have the vapor barrier, if you will, on the wrong side of the wall. And good luck trying to explain this to the homeowner. In the state of Minnesota, they, about 5 years ago, made it illegal to put poly in the basement. They made it a requirement that you have continuous insulation on the outside of the wall. They are exactly the same climate zones as we are, and worse. I mean, what is it? Duluth is zone 7A, 7B. It's the same as Edmonton.
Mm-hmm.
So sorry, I just had to say this because sometimes we talk about these things, but until you're called into a home in Canada and you're asked by a homeowner, why is this happening? And you say, well, that's a code built wall. That's not good enough.
Mm-hmm, mm-hmm.
Anyways, all right, I'll get off my soapbox. Go ahead.
Well, that's great. Those examples are always like so useful. And I have one on my own coming up. Wait, what did I do? I didn't share my screen back yet. There we go. Okay, so here's what's going on below grade. What can happen in the summer is that we can have warmer temperatures outside the foundation wall. If this is the concrete, this is a stud wall with poly. We can have warmer temperatures outside, especially near the ground, than we have inside.
Mhm.
We also, if we have damp soil here, can have 100% relative humidity trying to drive through this wall system. And what happens is our relative humidity doesn't drop at all until it hits that poly, and it's still at 100% by the time it gets to the backside of that poly. And the other thing to look at is when we look at, we saw these comparisons of walls above grade. In a below grade wall, this is pretty typical for vapor pressure differences between inside and outside. So if our interior vapor pressure is the same, but our exterior vapor pressure is much higher for much longer of the year. And actually it's now reversed. Now we have higher vapor pressures outside than we do inside for 76% of the year in this example.
Wow. In the basement. So above grade, we dry to the outside. Below grade, we're drying to the inside. We got the poly on the wrong side of the wall.
Yeah. And where you see photos like you had is when there's just a lot of moisture in this in the soil outside of the concrete wall, which is a lot of places we build. Yeah. Here's my example of that same thing. I saw all this rust happening at these bands, and what was happening is we were getting condensation on the backside of the what we call the diaper here. The
yes, yeah, because it gets wet and it smells.
Insulation attached to poly. It was running down and collecting halfway down because of this little drip edge here. It was rusting the banding and then eventually spilling out onto the floor as rusty water. Yeah. So same thing. In this case, there wasn't a stud wall. There was just this diaper that was used. And there was a known sort of high water table in this neighborhood, and the soil was quite moist outside, and that was the result. So how do we fix it? I think Andy already mentioned this, which is great. He mentioned actually exterior insulation on the outside, which is awesome, which will work great. This example shows putting a layer of rigid foam insulation on the interior of our foundation wall before we put our stud wall up. And really the big thing that does, it allows, makes our vapor drop and humidity drop occur across this layer. We still might have 100% relative humidity right here where the concrete meets the foam board, but both of those materials can handle moisture. So it's not really a big deal. Once we get into the wood and materials that we're worried about, our RH will be very low.
Okay.
That's how we
it's interesting. I remember John, Mr. Straub, good old John saying, you only have two options below grade. You can either throttle it back, which is what you're talking about, or you need to let it through, which is a variable perm smart vapor retarder, right? You really sort of limited to two things, or a little bit of both.
Right. For sure. That's another good option to look into also. So the other issue that we can come into with using poly as opposed to another vapor retarder that is more open is that we risk sometimes creating a moisture trap in our walls, especially if we have foam board insulation on the outside of our wall and poly on the inside. If this gets closed up, this wall gets closed up during construction, and there's high moisture content in the studs or in the sheathing, how does that water get out? It's going to take a long time. And so I did another quick WUFI analysis, hygrothermal analysis, to show what's going on. So the blue line here is what happens if we have no vapor barrier whatsoever. And you can see that you do get quick drying when there's no vapor barrier at certain times of year, but you also get a lot of wetting in the winter because now we've got the problem of our vapor flow from inside to out problem. So this is an above grade wall, by the way, as opposed to what we were looking at before. So what can we do? Well, we could replace our poly. Well, we could put poly in. We put poly in. I think that's the orange line here. As you can see, it takes 2 years of drying before it gets back, almost 2 years before it gets below 20% relative humidity. So quite a bit of damage could happen in that time frame. If we were to use vapor barrier paint, we actually don't see much difference in this case. So allowing a little bit through, because it's not a variable vapor barrier, it doesn't help us out much. But where we do see a big difference is when we move to the smart vapor retarder membrane, which is in gray. As you can see, we get much quicker. We're down below 20% moisture content after less than a year, and it stays below 20 after that.
Yeah,
So that's
you know,
one
it's interesting. We've seen scenarios, Trevor, where we take just a little bit of that smart vapor barrier, that variable perm, and we actually just tape a 2-foot section into the existing poly, and the entire wall actually starts to dry just from that little bit of application.
Interesting.
Yeah.
Yeah, and there's different approaches being used for unvented roofs with allowing vapor vents as opposed to air vents. There's some really interesting stuff going on there.
Okay.
What's this green line though? Just really interesting. If we replaced this foam board insulation with a rigid mineral wool insulation, this is how fast it would dry out. Much more quickly. And the reason is because we have, remember, the majority of our vapor drive is to the outside. So that's going to happen more quickly than this moisture could dry to the inside.
So you started this at about a 30%. So that's so that you're like you're saying, this is a newly built home. The wood is wet. It's got higher moisture content, and then you close it up. And now what do you do with that? Okay.
Where does it go, right?
Where does it go?
The same concept could occur if you had a window leak in one area, right?
Imagine that.
Except you don't only get drying, you get wetting and then some drying, and then some more wetting and some more drying.
Right.
And so this moisture trap can be an issue there too. I don't know if you've seen any windows that leak, but I've seen a few.
Yeah, it happens. Another topic for another day.
Yeah, so we're getting tight on time. I'm going to really quickly talk about what the codes say. Okay, so we kind of talked about on OBC, NBC, and really they're saying, you need to have a barrier for a vapor diffusion. Okay, pretty simple there. Well, what is that? Vapor barriers shall have a permeance not greater than 60 nanograms. Okay, we talked about that a bit. In this case, it's important to note that it's using dry cup. There's a few other caveats were really simple, that different types need to meet different standards. No big deal. One interesting thing though is we do specify that insulation that's functioning as the vapor barrier must be sufficiently thick so as to meet the requirements of sentence 1, 60 nanograms. So we do get specific there.
Do you want me to show that picture real quick of that one? So that's the, we got just a quick slide here. What Trevor's talking about is what's referred to as the inboard outboard ratios. So if you have insulation that is considered a vapor barrier, like a XPS type 4, don't get too concerned. For 40 years, we've known that if you do have that, you just need to have enough of it on the outside. So the inboard outboard ratio is 925/5.2. Here in Toronto, here's an example based on heating degree days. It's saying that, if you have at least 20% of your total thermal value as the continuous layer of insulation on the outside, it has to be at least 20%. And so if you have a 2x6 wall with R22 bat and you put R5, a low perm XPS, it's actually 26%. So you should be good. And this is based on that premise that, okay, it's controlling the dew point. Is that right, Trevor?
That's right. Yeah. So that is protection against air leakage condensation and vapor flow condensation.
Okay. And we sometimes get this.
Assuming that we didn't close up a wet wall.
That's right. Assuming we didn't close a wet wall. That's right. That's right. Good. Thank you.
Yep. No problem. So, double click it. So there's not a lot of specificity to the OBC, NBC. The only other thing we see is that products that are vapor barriers shall protect the warm side. And then they get interestingly specific. Well, I don't know why.
Sufficiently close.
Then they say it's got to be on the warm side, but then they later say it has to be sufficiently close to the warm side to prevent condensation. And it says the exact same thing about a vapor barrier that's the same as the insulation and that's separate from the insulation. So
Trevor, just a question. Sorry, I know you're running short on time. If we had in the basement, like you showed, the layer of low perm rigid insulation up against the wall on the inside, and then we have a stick frame wall with insulation in it, the low perm insulation acts as a vapor throttle, which you showed that slows it down. Could that not be deemed to be the vapor control layer as well?
Yeah, that absolutely is, right? The interior face really could be considered the vapor control layer
Okay.
of that wall system. It's all how you define it. And then is that the interior face of the XPS sufficiently close to the warm side?
Sufficiently warm, right. And it's so hard to do that, right? And the lack of, a woofy model and a third-party engineer in your corner, it's like, yeah, okay, good.
No, yeah. So it gets into the tricky wording there, and code officials don't like tricky wording for sure. So as simple as the OBC treats vapor flow, as we talked about, there's actually some really interesting stuff going on in the States related to the IRC, the International Residential Code. Way more specificity to how they deal with vapor flow, which is, I think, awesome.
And we have to remind people, you were talking about this. You remember those old building science folks, Gus Handegord, Neil Hutchins,
yeah.
John Timisk, and now let's lump Joe Steebrook in there too, right? Like Joe is in the US having an influence on this IRC code, having that same Canadian background, but now it's a Canadian with Canadian building science having influence on a US code. So it's worth us looking at. Yeah,
absolutely. This is like, Bobby Orr playing for the Boston Bruins. We wish he played for Toronto, but he doesn't.
That's right.
He didn't. Anyways, so one interesting thing I noticed is that they specifically say an approved design using acceptable engineering practice for hygrothermal analysis shall be used as an alternative, which is interesting. There's a few exceptions to the fact that you need vapor retarders, and one is basement walls and below grade portion of any wall. And for reasons we talked about, right? There's a few other things. They have a very specific thing about spray foam plastics and using them as different class vapor retarders, which I'll talk about, I think, next. Yeah, so here's one of the more interesting things is they don't say there's a vapor barrier. They say there's 3 classes of vapor retarders, class 1, class 2, and class 3.
So they've got away from the fact we're not talking full stop. We just want some control.
Exactly. Okay. And some apply in different conditions as we see. But yeah, a class 1 is what we think about, which is equal to or less than 0.1 perms, which is like polyethylene, and only really vapor closed materials can do that. Between 0.1 and 1 perms. And 1 perm is right about what the OBC asks for. So the high end of our code would be a high end of the class 2. And so they give some examples of what those are, including vapor retarder paint and other materials. And then they also have a class 3, which is more like latex paint and other materials with a perm rating between 1 and 10.
So not even vapor barrier paint, just latex on drywall. Yeah.
There's probably very few areas in Canada we'd be able to use a material like that, but it's good to know it's there. And depending on how much exterior insulation we use, maybe we could get into something.
Okay.
So they get very specific about that. And then they get specific about climate zones and which of these classes are permitted in different climate zones. So for example, in the coldest climate zones, class 1 and 2 are permitted, but not class 3. In classes 1, so zones 1, 2, 3, and 4, which are warmer climates, you're not allowed to use poly. Not permitted.
There you are.
Yeah.
And so zone 4, for anybody that's from BC, take a look at your ASHRAE charts. If you're in Victoria, you're pretty well sitting in zone 4.
Isn't that interesting, right?
Yeah.
The other thing that jumped out at me is they specify that these the permeance numbers they're using are based on the wet cup method versus the dry cup numbers that we use. So now it's not a direct comparison again to what we're doing. Yeah. And they have good reasons for that. I read their reasons for it. I think there's maybe arguments for both, but that's something we could talk, I think we should look into for our codes in the future. They give some very specific examples of each class of material right in the code, which is cool. And then this one blew my mind is that for each class 2 and class 3, they say in different climate zones, how much exterior insulation you would have to use in each climate zone from 3 to 8 so that you can use a class 2 vapor retarder.
So
in
let's go Toronto. It's not the center of the world, but zone 5. What are they
Yeah,
saying?
we're in zone 5, right? So in Toronto, you would have to use, over a 2x6 wall, you'd have to use R5 continuous insulation.
Huh.
Then you could just use a class 2 vapor retarder like Vapour Barrier paint.
There you go.
Right? Now let's go, like, I'm heading up to Iqaluit next week with Mark,
Oh, wow.
my buddy, who's I think on this call. If you are, how's it going? If we were to try and use a class 2 vapor retarder in somewhere like Iqaluit, we would, over a 2x6 wall, we'd have to be over R10. Actually, I think it'd be quite a bit over R10 for that. But they get very, probably their climate zone 8 would be, well, that might be Alaska. I don't know. I'd have to look that up. So for each climate zone, you're allowed to use a class 2 vapor retarder if you use enough exterior insulation.
Okay.
And then guess what? There's even a table that says you can use class 3 vapor retarder in different zones with even more exterior insulation. So again, zone 5, if you want to use a class 3 over a 2x6 wall, you'd need R7.5 in Toronto.
So if you just wanted to use, if you just wanted drywall and latex paint to serve as your vapor control layer, and if we had this system, we would be able to go and say, then I just need to put R6 on the outside, and or R5 or R10.
And that's pretty much what that example I showed in Toronto was, where we had no vapor barrier. I called no vapor barrier, actually was a class 3. It was latex paint and drywall.
Okay.
So these are actually relatively conservative, which is good. Some of the modeling might show that, oh, you could squeak by with R5 instead of R7.5. But when it comes to code, I'd rather see the 7.5.
Yeah, gotcha. Yep.
To be safe for other reasons too. So that's really interesting for me, what's going on in the States on this topic. And they're not ahead of us in many ways from a building science perspective, but here's a way that they're really gotten ahead of the game. And I think that we should be looking at this.
But again, remembering that individuals responsible for this actually were, you know, they should be on the Canadian team, right?
That's right. That's right.
Very good.
They're using all our best knowledge and information to improve their codes. So we should do the same.
Yeah.
So real quick summary, do we need a vapor barrier? No, we don't need a vapor barrier, but we do need vapor control. There's a lot of things it depends on, right? It depends on climate, interior conditions, what materials are on the exterior side of the wall. Is the wall above grade or below grade? You know, how much exterior insulation are. There's a lot of things we need to consider, but we don't need a barrier to vapor, but we do need to control it.
Nice. Well, Trevor, I followed you on a little piece of this today. It's going to take a while to digest this, but let's dive into questions. We have about 10 minutes. Are you okay if we go over by 5 minutes, Trevor? Are you okay with that?
Yeah, it's my fault we went over, so yeah.
No, it's good. That's good. This could be 2 or 3 sessions. So I'm going to start with the Q&A. I don't know that we're going to get through all of these, but let's start with the first question. Rob Cardinal says, do you have any experience with vapor barrier paint primer coatings applied to gypsum, pros or cons?
So one experience that we do have is that we found from early testing, we haven't done this testing in a while. Back in the day, we did test vapor barrier primers on drywall. Yeah. And they don't work as well as they say they work, typically, because they get absorbed into the material. When they test it, they put a certain level of thickness of material on a piece of poly, let it cure, take it off, and test it. But what we found is that if you apply it to drywall, I think 2 coats, or maybe it was just, I forget if it was 1 or 2 coats, but it doesn't perform quite the same way, not as well as a vapor barrier. So my caution there would be 2 coats of vapor barrier paint if that's your approach.
Okay, good. Excellent. Grant Leclerc just has a interesting question. He says, you know, is it water? This was early on. Is it water vapor only? What about other types of, you know, carbon monoxide, carbon dioxide, methane, concrete, off-gassing, things like that? I suppose they could also diffuse. I think that's the point. They could also have diffusion like water vapor.
Absolutely. Every material has a certain permeability to every molecule.
Yeah.
We're focusing on those water molecules because they get in our walls and mess them up.
Okay. Good. Jacob Nichols asked the question. So, and again, you covered this. Good. Was the dew point and vapor pressure, are they directly related?
Yeah, they're directly related. Yes. No, because dew point is related to temperature.
It's related to temperature. That's right.
Yes, the temperature is the thing that connects vapor pressure and relative humidity, and dew points meet in the middle.
So maybe a bit of yes or no. Yes, that's right.
Yeah.
We did. Yeah.
Yeah, there's a relationship, but not,
Yeah, I like that. You know, the relative humidities are on curves between temperature and the temp and the amount of water in the air. And then over to the right, you actually have the pressure on the chart, the up and down of the chart.
And what I didn't talk about on the psychrometric chart is they actually have dew point numbers too. So you could go from 20% R, 20% or 20 degrees Celsius, 60% RH, and go over to what's the dew point of that air.
Right.
So that's on that chart too. There's a lot on the chart.
And that's how the guy that invented it used it, right? Willis Carrier, when he made that, he was condensing out water. He was you know, Bridget O'Flaherty says, do smart, or what's in Canadian codes being called variable perm vapor barriers, do these smart vapor barriers actually accommodate the ranges from summer to winter, so heating and cooling changes?
They react to relative humidity.
Okay.
And relative humidity is almost always inversely related to temperature. So
right. Okay. Okay. Richard Martin says, how do we eliminate condensation behind poly in the basement wall? I think you covered that well. It's a good question. That's the same one as Stephen Parks asked, sort of the same thing.
Yeah, a couple different ways.
So you showed us put a lower perm, so either throttle it back or let it through with a smart vapor retarder. Okay.
Yep.
Jacob Nichols, does XPS not reduce an R value when it is moist? I believe that this gets worse over time. No? Question mark?
It does, but it would only get wet if it was sitting in water, like literally. Right. Yeah, it won't absorb. It absorbs water so slowly. The only time we see this as an issue is in roofing systems, where like inverted roofs, where the XPS is sitting in water for years and getting baked by the sun, and it will take up water, but very, very slowly. In a vertical situation, you'll never have to worry about it. The water would always drain away before it got absorbed.
Okay. It is an interesting point, though. You know, you look at XPS or EPSs; they have different water absorption rates. So that's it's good. Dave McCauley said, Dave's a great architect in the local area here. It's good to have him on. He says, why wouldn't condensation occur with interior foam at the joints, and on concrete I've seen a lot of mold on the foundation? I don't know if I quite get that question, David.
Like if it's cold, if there's a cold spot at the joint,
It seems like it
there.
Yeah.
But we definitely would want to tape all the joints in that scenario, in the basement wall. Assume we're talking about the basement wall with the XPS against it.
It could be.
Yeah, we definitely want to tape that and not allow the boards to move too much, because they're on the warm side. They shouldn't see a lot of temperature difference.
Okay.
Like they would if they were on the outside of a wall. They would see quite a bit.
Okay.
Yeah.
Feel free. I'll have David maybe type that in a little more detailed if he wants to, and we can try to get to it. Terry Pekka, head of director of sort of building science construction for Habitat Canada. It's good to have Terry on. He's works with a lot of builders across Canada. He said, can you talk a little bit about, similar to air tightness, can you speak to the consistency of the air/vapor barrier over the building envelope?
That's here's the example I give is if we're talking about continuity. When we talk about air barriers, continuity is everything.
Yes.
When we talk about vapor barriers, continuity isn't that important. It's not as important. And Joe Stiebrick's example is if he used to put a poly vapor barrier down below a concrete slab, if you were to walk on it with golf spikes, it would still work basically the same as it would if you didn't do that.
As a vapor barrier.
Because it's not the air barrier, it's only the vapor barrier.
Right.
But in your wall, if it's both an air and a vapor barrier and you poke a hole in it, it's going to be a real problem from an air leakage standpoint, but that's not going to be an issue from a vapor flow standpoint.
Okay. So it really does. Yeah, that's good. Keko Gata says, have you done any research or comparison for SIP walls between SIP structurally insulated panels and 2x6 walls? Trevor, you've got some experience with that.
I've got quite a bit of experience with SIPs. They act more like a monolithic wall than they do act like a stud wall, which is good from a vapor flow standpoint. The problem or the challenge with SIPs is what happens at the joints. And it's really an air leakage question, not a vapor flow question. I would never be worried about vapor flow issues with SIPs, but I would be concerned with air leakage.
Okay. Anastasia has writes a long, just a bit, tells a little bit about her own experience. I'm just conscious of the time we've got here. So her questions pertaining to her own home, 80 to 100 years old, plaster, additional layer of drywall either side, bought the house 4 years ago, has blown cellulose. She learned about vapor barrier paint from Ed Marianne. She would love to know what is the name of the vapor barrier, vapor retarding paint?
There's a lot. Every manufacturer makes one, to be honest. Like all of your big paint manufacturers make one. So, and they all act basically the same. The other thing I would mention is if your house is made, has plaster walls like mine, it probably has, and is old, almost as old as mine, it probably has several layers of oil-based paints on it. Probably lead too, but oil-based paints that will be more effective as a vapor barrier than vapor barrier primer would, a modern vapor barrier primer.
Oil-based, interesting. Yeah, no, that's a really good point, Trevor. Good. Oh boy, I'm trying to keep up with these here. So Pete says, what impact to dryability does a standard painted drywall assembly have if you include it in adjacent to a smart vapor barrier like membrane? So let's assume he's saying swap out the poly with a smart vapor retarder.
Right. That's the exact example I gave in that one table that showed drying from 30% downward. That was a wall. Yeah, that was a wall with one of them versions of poly. It helped. Yeah, it helped. Keeping in mind that it's faster to dry a wall outward than it is inward. Right.
Yeah. If we do not, Fauzi, I think that's, pardon me if I messed your name up there. If we do need a vapor barrier, what will be used as an air barrier instead? I love it. First of all, he separated the two.
Yeah, that's the great first step, right?
That's right.
Yeah. So if we separate air barriers and vapor barriers, and we use enough exterior insulation that we don't really need an interior vapor barrier per se, other than maybe vapor barrier paint, let's say.
Right.
Then we can use the sheathing or membrane on top of the sheathing as our air barrier. That gives us a whole other layer of options.
Right.
To use an exterior air barrier on the outside of the sheathing.
I like that, Trevor. And that's what we're seeing. I think this is why it's coming up more often, is if we are going to do an exterior air barrier with a house wrap or a certified air barrier system on the outside with the insulation, what about this poly on the inside? And now we're asking questions about what purpose does it serve? So maybe we should all hold our right hand up in the air today and swear that we will never call it a vapor barrier again. We will call it an air barrier and only use the term vapor barrier if that's exactly what it is. Good. Rick says, can you please speak more to the plywood OSB, thinking garage ceiling with bonus room above? Oh yeah. So that was that comment about the fact that the OSB or plywood is a vapor barrier, but only under dry cup conditions, right?
Which is, every building should be under dry cup conditions. If you have enough liquid water around or high humidities, you have another problem. But assuming we don't have a water intrusion problem, plywood or OSB will act as a perfectly fine vapor retarder in our climate, in a lot of climates, even worse climates in Toronto. Yeah.
It's almost like a smart vapor retarder in some
No,
cases.
it totally is. It is smart.
Yeah, yeah.
Yeah.
I don't know about this one. This is from Guy. He says, have you examined Saber's work on perm and R value effect on the mold index? It seems to validate that perm has little effect on mold index as long as the insulation CI is high.
I don't, not familiar with that. But
Okay.
there is definitely a relationship between vapor flow and temperature. And so if you're talking about CI and using more continuous insulation, you're reducing your risk
Okay.
of mold growth, for sure.
I'll have to look into that research a little bit. That's interesting. Robert says, consider a block foundation that might experience minor water infiltration during the wet season. So CMU type foundation, can't dig exterior, can't do anything to add a drainage layer. Maybe can add one on the inside of the foundation with, could I do it on the inside with continuous rigid insulation? You know, what will be the effect of the vapor throttling?
Right.
So scenario is can't do anything outside, existing home, lots of water, can't drain it, wants to insulate the inside.
All I would say is if from a vapor standpoint, the 2 inches of XPS on the inside will take care of you, no problem. But if you have a known water problem, liquid water problem, then I would put a dimple sheet on first and drain it down to the footing drains before I put my XPS on.
So trench out an interior drain then somehow once it's on the inside. Yeah, that's right. Good, good. All right, folks. I don't know if we're going to be able to hit all these questions, so bear with me, and I apologize if I don't get to yours. Does using closed cell foam in the basement, so closed cell, assuming like a 2-pound, with the studs away, so studs away 2 inches, spraying it, let's say 4 inches to the foundation wall behind the studs, does that solve the winter or that reverse vapor drive scenario?
Yeah, that would be almost identical to my the concept of 2 inches of XPS, 2 inches of closed cell foam would be almost the exact same hygrothermal performance.
Okay, so again, acting as a vapor throttle, you know, we often see that in retrofits, right? They go to the basement, closed cell foam, throttles back that. Okay.
Yep.
All right, folks, we might have to wrap it up today. I'll tell you what we're going to do. I'm going to have Stacy just collect the rest of the questions. And between Trevor and I, we'll put our heads together and see if we can answer some of these for you. But really good questions. I mean, it's one of those conversations we can continue. So I'm going to just hop back on here real quick. We've got just some parting slides. So let me get back to my right slides here. So if anything, if we come out with anything today, maybe Trevor, it's fair to say that you know, we understand that air barriers are more important than vapor barriers for controlling moisture. However, we still need to maybe still be serious with vapor control. We know that there's better or more appropriate options than poly. And maybe there's some new ways that our building code should start to call out vapor control layers. And you've given the example of maybe what they've done, you know, with the IRC in the US, which again was premised on a lot of Canadian work. So I don't know if you want to leave us with any thoughts on that part, Trevor, or
yeah, it seems like they've done a lot of the heavy lifting on that from the IRC standpoint, that we can use that as a template. I think we need to look at it in our context. Obviously, we need to look at it in terms of, does it make sense to use dry cup or wet cup? Should we do all of the climate zones make sense to us? Do we need more of them, different ones? So we're gonna have to redo some of the analysis and things, but I think the template is there of things that need to be covered in the code that aren't.
Okay, good, good. All right, Trevor. Well, thank you, folks. Just so you know, as we wrap up today, keep your eye out too. If you don't get have our on our mailing list for our Canada Builders Digest, we send out quarterly. It's got building science stuff from folks like Trevor and others on it. It's specifically for home builders. It's pretty cool. It's free of advertising. Just sign up today. The other thing I'll just remind you of is that the next Enbridge webinars are coming up here. We have one on the construction, heat and appliance commissioning. That's very specific to Ontario and contractors and builders in the area for the commission heat refresher. And then another deep dive, part 8 of our Critical Canadian Home Building Science is actually going to be our own Gord Cook and Angela Bustamante. And they're going to be talking on October 20th about how do you design for occupant comfort. You know, it's often been said, I think Robert Bean, you know, our dear friend Robert Bean from Calgary, excellent, you know, ASHRAE distinguished lecturer would say, if we actually put in the code that you had to design to the parameters of thermal comfort, we would instantly solve the energy issue. Okay. That's sort of cool. All right, folks. Well, Trevor, thank you again. And folks, thanks for your questions today. I think we're going to have to wrap it up. And like I said, we're going to try to get you some answers. And likewise to some of you in your comments, happy Thanksgiving, and everyone have a safe long weekend coming up too. Thank you very much.
Thanks, everyone. Thanks, Andy.
Thanks, Trevor.